Before an engineer ever picks up a tool or draws a blueprint, they have to know exactly what they're trying to build. That's why defining the problem is the very first step in the entire engineering design process. Think of it like a detective. You can't solve a case unless you clearly understand the crime. We're tackling the Common Core standard that focuses on this critical initial phase, ensuring that the work we do actually addresses a real-world need or want. It sets the foundation for everything that comes next. So, what exactly is a design problem? It's not the same as asking a science question, like what causes a solar eclipse. A design problem is about creating or improving something, physical or procedural, using technology. For example, the problem isn't why does food spoil, but how can we design a better container to keep food fresh for longer? It always needs a goal, something we can build or invent to move from a current, problematic state to a desired, solved state. Every great design starts with understanding who needs help. We call these people stakeholders. If you're designing a new, safer helmet, your stakeholders are the athletes, their parents, and maybe the sports league. Their needs, the athlete needs protection, the parent needs affordability, are the starting point. If you don't talk to the people who will actually use your solution, you might end up building something brilliant that nobody actually wants or needs. Once you've identified the need, you write a problem statement. This isn't an essay. It's a short, powerful sentence or two that sums up the entire challenge. It keeps the entire design team focused. A great problem statement is almost always framed as a question, like, how can we design a cost-effective, portable solar charger that can fully charge a smartphone in under 2 hours? It clearly states the what and suggests the why. Now let's talk about success. How do you know if your final design actually solved the problem? That's where criteria come in. Think of criteria as the list of must-haves, the standards the solution must meet. If you're designing a better pencil, a criterion might be, it must be comfortable to hold, or it must write on both paper and wood. They define what a successful outcome looks like. On the flip side of criteria, we have constraints. These are the limitations, the walls that restrict your design freedom. Imagine trying to build a magnificent castle, but you only have 5 sticks and an hour of time. Those are constraints. In the real world, constraints are things like your budget, how much money you can spend, your time, your deadline, and your materials, what you're allowed to use. You must always design within your constraints. It's easy to confuse criteria and constraints, but they're different sides of the same coin. Think of it this way. Criteria are your goals, the things that make your design good. Constraints are your limits, the rules of the game. A great engineer doesn't just meet the goals, they meet all the goals without breaking any of the rules. A successful solution satisfies all criteria within the established constraints. Before you finalize your problem definition, you have to do your homework. This means research. Are there already solutions out there? What works about them? What fails? Researching existing technology, talking to experts, and gathering data is key. If you skip this step, you might waste time designing something that already exists, or something that has failed for known reasons in the past. It's about building on the knowledge that's already out there. The target user is everything. If you're designing a new type of water bottle, the needs of a professional marathon runner are completely different from those of a third grader. The runner might need insulation and a quick sip lid. The third grader might need a spill-proof top and a durable exterior. By zeroing in on your specific user, you can tailor your criteria to their exact needs and ensure maximum success. When defining a problem, you need to set clear boundaries or a clear scope. If you define your problem too broadly, like how do we stop climate change, you'll never finish. That's too big. You need to narrow the focus. How can we design a personal composting system for apartment dwellers? A tight scope makes the problem manageable, measurable, and ultimately solvable. To truly know if your solution is better, your criteria need to be quantifiable, meaning you can put a number on them. Instead of saying the bridge needs to be strong, you say the bridge must support a load of at least 15 kilograms. When you use numbers, your testing is objective and clear. You've either hit the 15 kilogram mark or you haven't. This eliminates guesswork. Not every requirement can be measured with a ruler or a scale. Sometimes criteria are non-quantifiable or subjective. Think about things like aesthetics. It must look modern and sleek, or user-friendliness. It must be intuitive to use. While these are harder to measure, they are still important. You usually test these by asking your target users for feedback and rating their experience. Let's talk money. In almost every design project, the budget is a major constraint. You might have a brilliant idea for a robot that cleans your room, but if it costs $10,000 to build, no one will buy it. Real-world engineering means designing a solution that is not just functional, but also cost-effective and financially viable within a set budget limit. Time is always ticking. The time constraint is the project deadline. This restriction forces engineers to be efficient and prioritize. You have to design something achievable within the given time frame. A complex 5-month project can't be completed in a 2-week window, so you have to adjust your criteria and scope to fit the schedule. The materials you have available can heavily impact your final design. Material constraints can be about what's physically accessible, like only using recycled plastic, or what's permissible, like a rule that says no hazardous chemicals can be used. These constraints force you to be creative and resourceful, often leading to very innovative, non-obvious solutions. Safety is so important. It's both a constraint and a criterion. As a criterion, your solution must do what it's supposed to do in a safe manner. A toaster shouldn't catch fire. As a constraint, your design must adhere to all government or industry safety codes and regulations. You can't design anything that puts your user or the public at risk. Safety is always non-negotiable. One of the toughest parts of defining the problem is dealing with competing constraints. This happens when one requirement pushes against another. For instance, you might want your product to be extremely durable, a criterion, but also extremely lightweight, a constraint. You can't always have both perfectly. This is where engineers have to make trade-offs, deciding which criteria or constraint is most important to the target user. The problem definition you start with is rarely the one you finish with. It needs to be revisited and refined. As you research and maybe even do a little preliminary sketching, you might realize your budget is too low or your deadline is impossible. It's perfectly okay to go back and adjust the criteria and constraints. This flexibility is a sign of good engineering, not failure. Modern engineering demands that we think about more than just function. We need to consider ethical implications. Does your design create pollution? Does it exclude any group of people? Defining the problem now means setting criteria for social responsibility and sustainability. A successful design must not only solve a user's problem, but also benefit society and the environment. Once you have your clear problem statement, your list of measurable criteria, and your comprehensive list of constraints, you've completed the most critical first step. You now have a solid foundation. This finalized design problem acts as your compass, guiding every decision you make moving forward. Only now can we confidently move on to the next phase, brainstorming and generating potential solutions. Great job, engineers. Now the real fun begins.